honor students, this is concept 2 notes all about classifying reactions. So hopefully all of this majority of this will be a review from what you've seen in the stations that we already should have done in class. And we're just going to kind of review that, and I'm going to add on a few extra things for you as honor students that I want you to be aware of. So chemical reactions in general fall into one of 5 categories, and we're going to see today that there are other specifics that you can kind of get into. I'll cover a few extras for you, but these are the 5 general categories. Reactions can be considered synthesis reactions, decomposition, combustion, single replacement, or double replacement. And the reason this matters and the reason it is helpful to be able to classify reactions is because then if you know the type of reaction and you see the reactants, you can then predict what products will form. And that's something we'll be doing at the end of this concept. So stay tuned for that. So we're just going to kind of walk through each of these. I'm going to summarize what you need to know about each, and I'll give you some examples that I think will be really helpful. So first, synthesis. This is also known as a composition reaction, a combination reaction, or a formation reaction. I've seen it all these different ways in different texts. Typically, though, the most common way to refer to it is as a synthesis reaction, and that is just when we're taking 2 or more reactants and we're going to combine them to form a new compound. So A plus B would yield AB, reacted together, chemically combined together. This is our general equation in purple. So for example, this equation that is familiar, this reaction is one we use a lot as an example in concept 1 notes, but solid sodium reacting with chlorine gas to make solid sodium chloride. That is 2 becoming 1. That is a synthesis reaction. Now, one thing to make note of, some kind of special notes for each of these, which we'll do after we kind of go over the general equation and an example. Things that I want to highlight to make sure you notice as you're looking at these. When an element combines with oxygen, so when oxygen, is one of our reactants here, it's going to produce an oxide, which is a binary compound with at least 1 atom of oxygen. Okay, so for example, when solid carbon reacts with oxygen gas, it's going to make carbon dioxide, okay? That's our oxide here. Now, if certain metal oxides combine with non-metal oxides, they can make salts. So we have calcium oxide here, reacting with sulfur dioxide here, it's going to make calcium sulfite, which is a salt that we see here. So that's another kind of thing you can keep your eye out and look for. Now, a decomposition reaction is just the opposite. It's when one reactant produces 2 or more simpler compounds, or they decompose and break down into 2 or more things. So just the general equation is the opposite of synthesis. It's AB yields A plus B. So for example, calcium hydroxide breaks down or decomposes into calcium oxide and water vapor. Now you may notice this little triangle up here. This is important. Most of these reactions only take place when a certain amount of energy is added. Usually that energy is in the form of heat or electricity. So like if you put calcium hydroxide in a beaker on a lab table at room temperature, it's most likely not just going to decompose sitting right there. You're going to have to add energy to make the reaction happen. Remember our collision theory. You're going to have to add something to make them collide enough that there will be a change that will occur and a chemical reaction that will occur. So the way we notate this is typically with something above the arrow, because for instance, for this reaction, for the decomposition of calcium hydroxide, there has to be heat. And we represent that with the delta sign, the change in sign. And we put it above the arrow because heat is not a true reactant or product in this reaction, but it is necessary. You may be familiar with this from biology when you learned about photosynthesis, that carbon dioxide and water react with the help of sunlight. You should have been writing sunlight or sun over your arrow to make carbon dioxide and water, to make glucose and oxygen. Okay, so that's hopefully something you've seen before. Now, another thing we'll see besides just heat is electricity. And so when that happens, we'd say that this is an example of electrolysis, which is the decomposition of a substance by an electric current. So for example, we can take liquid water and decompose it into hydrogen gas and oxygen gas with an electric current. So we would write electricity above that arrow. Now, there are a few more specific types of decomposition. It can be hard to know, okay, well, how will this break down? What will it end up making? How am I supposed to know that calcium hydroxide makes calcium oxide and water? Well, we have some patterns we see here, and so that's what we're going to specify now. So for instance, the decomposition of metal carbonates. So any sort of metal with like a carbonate, CO3, polyatomic ion. It's going to make a metal oxide and carbon dioxide gas. So for example, calcium carbonate, with heat will decompose in a calcium oxide, that's my metal oxide, and carbon dioxide gas. Okay, so you'll always see that with metal carbonates. Now, metal hydroxides like CaOH2, okay, that will always make a metal oxide and then it'll make liquid water. Okay, with the exception of group 1 metals, we don't see that there. So for example, calcium hydroxide will decompose with heat to make calcium oxide, that's my metal oxide, and water. Oop, I need to change that to liquid. I'll do that next. Okay, metal chlorates. They will break down and to make a metal chloride and oxygen gas. So for example, calcium chlorate will break down. It needs, here we have to have, sometimes you have to have a catalyst. In this case, it's manganese 4 oxide. That's our catalyst here, but that will make this reaction happen to make potassium chloride and oxygen gas. And another example is acids. So we learned how to name acids previously, but those will decompose and make non-metal oxides and water. So for example, we see this acid here, it'll decompose, it's going to make sulfur trioxide, and it's going to make water. Now let's talk about combustion. This is when a substance reacts with oxygen, and it's going to produce a lot of energy in the form of heat and light. Typically, we refer to combustion reactions as burning reactions because heat and light is what we see with burning. So you're going to have some sort of reactant reacting with oxygen and making a product or two. So technically, hydrogen gas and oxygen gas reacting to make water is a synthesis reaction, but you could also say it's combustion too. Typically, people aren't going to qualify this as combustion, though. They'll just say it's synthesis because that's what it more obviously is. Now, here's what you're more likely going to see. Many combustion reactions occur with a hydrocarbon, and it's a result then those hydrocarbons, when they react with oxygen, will always make carbon dioxide and water. So a hydrocarbon is just a compound made of carbon and hydrogen. So you have some sort of fuel source, which is your hydrocarbon. It'll react with oxygen, and you will always make carbon dioxide and water. This is what I'm going to expect you to identify as a combustion reaction for our purposes. So for example, carbon tetrahydride or methane will react with oxygen. It's going to make carbon dioxide and water. Okay, so you can see how this general equation plays out in this actual example here. That's a combustion reaction. Okay, the last two we're going to touch on are single replacement and double replacement. Single replacement reactions are also known as single displacement or single exchange reactions. And this is when one element replaces an element like it in a compound. So for our general equation, that's A plus BC will make B plus AC. For example, aluminum will react with lead 2 nitrate and make lead and aluminum nitrate. So the metal just replaced the metal in the compound like it. So they replace what is like it. Another example, this would be with a non-metal replacement. Chlorine gas reacts with potassium bromide. The chlorine will replace the bromine. So it results in bromine and potassium chloride. Oftentimes this occurs in an aqueous solution, which we can see here. And typically what we see is the most reactive metals can react with water, and they will make metal hydroxides and hydrogen. So that's important to note here. If you remember, the most reactive metals from learning about the periodic table are our group 1 metals. So they will react with water, and that's what they'll make. So like sodium is a group 1 metal. It's one of the most reactive metals. It will replace hydrogen in here, making sodium hydroxide and then hydrogen gas on its own. Okay, so that's something to take note of as well. So we've got our most reactive metal as sodium, we've got water here, and we've got a metal hydroxide and hydrogen being formed. Now let's talk double replacement. This is also known as double displacement or double exchange. This is when the ions of two compounds exchange places, typically in an aqueous solution, and we get two new compounds from it. So AB plus CD is going to make AD plus CB. One of the resulting products usually falls into one of three categories. So first, one of these products will typically be a precipitate, which is an insoluble solid that's going to form from the ions of two aqueous compounds. So when two aqueous compounds react and they make a solid compound, that's a precipitate. When you see this happen, you can specifically refer to this as a precipitation reaction, not just a double replacement reaction. It's a type of double replacement reaction, but it's specifically a precipitation reaction. An example here is aqueous sodium chloride and aqueous silver nitrates. They're both dissolved in water, react, and we get solid silver chloride. That would be our precipitate, and aqueous sodium nitrate. Another product we'll often see is an insoluble gas form. So this is when you see bubbles given off, you see effervescence. That's typically representing a gas being formed. So here we go. We have iron 2 sulfide reacts with hydrochloric acid. We get dihydrogen sulfide, or you can use your acid naming rules here, and we get iron 2 chloride. So this gas given off, those would be the bubbles that we would see. And then last, you can also see a molecular compound made like water. So hydrochloric acid and sodium hydroxide react to make sodium chloride and water. And when you see a reaction like this is actually an acid-base reaction or a neutralization reaction, which we're going to zoom in on a bit more. So again, like I mentioned, one of these special types of double replacement reactions I want you to know about. I already mentioned the precipitation reaction, but I also want you to be aware of a neutralization reaction, aka an acid-base reaction. So these are used interchangeably. So this is when an acid and a base react to form water and a salt. Now, we are not covering acids and bases in detail until Unit 9. Okay, so I don't expect you to know all the things about this. And one of the things that's kind of tricky about acids and bases is it's kind of hard to define them because different people define them different ways. But I'm going to give you what I think is the simplest definition for our purposes for now, and then we'll dive into this more in Unit 9. But for our purposes now, an acid is a substance that's going to make hydrogen ions when it's dissolved in water, and a base is a substance that's going to make hydroxide ions when dissolved in water. And again, these are also often easy to identify based on the compounds, which we'll look at in just a second. So a salt is an ionic compound made from the cation of a base and an anion from an acid. And then obviously you guys know what water is. So for example, hydrochloric acid is an acid because think, that's going to make, if this was going to be, dissolved in water, those hydrogen ions are going to break up from the chlorine ions. So that's going to make hydrogen ions. NaOH, sodium hydroxide, is a base because, again, when this dissociates in water, it's dissolved in water, it's going to be sodium and hydroxide ions. They'll make sodium chloride, which is a salt. The sodium came from hydrochloric acid, from sodium hydroxide. The chlorine came from hydrochloric acid, and they'll make water. So that's kind of where those four components come from. This is, again, it's still a double replacement reaction. It's just more specifically known as an acid-base or a neutralization reaction. So I want you to be able to identify those when you see them. So we're going to practice this. We're going to go back to everything we've already balanced, and we're going to classify those. And the more you do this, the easier it will be. But one last thing I want to touch on in the video is what I mentioned at the top of the video, which is predicting products. So if you're given the reactants and you're given the type of reaction it will be, the classification, you can then predict what will form. And this is because they follow really predictable patterns with the classification categories, but then also that some elements react more readily than others. And that's where their activity is going to be, you need to know it. And you'll know it because you're going to have a tool to use called the activity series. I'm going to give you this. It is a list of elements in the order in which they will easily undergo certain chemical reactions. So what we see is that metals are more active. They have a greater activity when they are losing electrons more easily. So think about your group 1 metals. They have only one valence electron. They're going to react a lot more readily than your group 2 metals that have 2 valence electrons, like calcium and magnesium. It's going to take more for those to react because they're going to have to lose more, whereas sodium is so close to being stable already on its own. Nonmetals go the other direction. Nonmetals that have a greater activity means they gain electrons more easily. So for example, fluorine. Fluorine wants that extra electron so badly. It only needs one to have that full outer energy level of electrons, whereas nitrogen needs 3. So it's not going to be quite as active as fluorine. And what we see when we look at the activity series is that it goes in order of most active to least active. So an element can replace anything below it because it's more active than any of the things below it, but it cannot replace anything above it. And this is useful, practically speaking, because you can look at a reaction like a single replacement reaction, and you can actually identify whether or not the reaction would occur, because the element or the substance that's on its own has to be more active than what it's replacing in the compound in order for the reaction to occur. So again, we are going to practice this as well, and I promise it will not be as scary once you get a little practice going. It'll actually be kind of fun because you'll start seeing the patterns and you'll be able to predict them more easily. So let's get to it.